I'm not going to talk about dark matter halos. I'm going to be talking about gaseous halos in fire simulations, especially because some of the topics related to dark matter halos were touched upon through my collaborators. TK talked about some of the stuff, Coral mentioned some of the dark matter stuff, and Phil as well. So this is work done in a large fire collaboration, and I'm going to show a lot of results from Sasha Muratov and Daniel Angles Alcazar specifically. All right, so standard motivation, which we cover many times. The universe is forming stars actively at all redshifts we can observe. High redshift galaxies look messy, typically. The largest ones might be more rotating, but typically they have high velocity dispersion, so they look like this. By late times, they look like more ordered, coherent, disky systems. But throughout this history of the universe, the typical volume of our universe is forming stars pretty rapidly. It drops by order of magnitude or so by present time, but when you look at spiral galaxies, they still form a lot of stars. So we have a couple of questions here. What drives the star formation activity of the universe throughout the cosmic time? And once we actually form stars, what do these stars do to their surroundings and to the galaxies themselves? And in this conference, we've seen many times that the cosmological inflows, it's a large driver of the cosmic star formation history, but as you will see in a second, it's also strongly modulated by outflows. So cosmological simulations show that supply of gas into early galaxies is driven largely by these cold filamentary flows of gas. And because the structure grows fast and almost all of the gas that drops in can actually get close or onto the galaxies, this fuel efficient gas accretion and efficient star formation of these early galaxies. At later times and in more massive halos, picture changes a little bit. Most of the gas that falls in shock heats to close to virial temperature. Some of this cold gas can still come at least to the inner halo, if not completely towards the galaxy. But we shouldn't think that when we have hot gas, the galaxies are dead, because some of the hot gas, especially in central parts, can cool onto the galaxy and can provide something that we call cold mode accretion. So we need to figure out exactly what's going on in these halos as well. And while we have overall picture of what's going on in terms of lower and higher mass halos and high and low redshift, there are still serious issues in terms of code we use, resolution, and feedback model to understand exactly how these things fuel galaxies over time. But that's only a fraction of the story, because if we let those gas inflow build up galaxies in our cosmological simulations and they form their stars, we end up with galaxies that are way too massive. So this is illustrated in this galaxy mass function. So this is the number of galaxies per unit volume of the universe as a function of stellar mass. This line here that I drew by hand, and it's probably off, but it's an illustration, it represents what would happen in all of the baryons in dark matter halos just turn into stars. This line here shows what's happening in the actual universe. This is the galaxy mass function by Belledol. And the results in the middle are actually results from cosmological simulations that have no or very weak feedback. So you can see that a large fraction of the available baryons actually cool onto the galaxies and form stars. But this fraction that cool and form stars is way too high when we compare it to observations. The way we should look at this diagram, we should match galaxies at the given number density. So if we match it at the high mass end, there is a factor of 2 or 3 offset in massive galaxies. So the hot halo maybe helps, but it doesn't really shut them down. So we need to figure out what to do here. And that's possibly done by AGN feedback in some sort of maintenance modes or something like that. The hot halo might enable it, but it doesn't do it on its own. But the problem is much more serious at the low mass end, which is where I'm going to concentrate in this talk. If you try to match things horizontally here, you see that there is an order or a couple orders of magnitude difference in the stellar mass that ends up in galaxies when you have some sort of feedback in the real universe or something, or you don't have any feedback in the simulation. So the standard picture is that there is a feedback from star formation. So stars provide lots of energy and momentum to their surrounding. And this can somehow affect galaxy formation at the low mass end and either eject lots of material from galaxies or prevent some of the materials from coming in the first place. So I'm going to focus a little bit on what's going on with this stellar feedback at the low mass end and mostly talk about galaxies lower than this characteristic mass of L star, above which I'm not really sure what's going on, but we need some mechanism to stop accretion there as well. So galactic outflows that are suggested as a solution to this problem at the lower masses are seen. They're seen at low redshift, but pretty rarely. we can only see them in the strong starburst galaxies. You can see local fountains very often, even in the Milky Way, but the large-scale outflows that go to significant fraction of virial radius are really seen only in the starbursts. So they're pretty rare at late times. But when you look at the high redshift, whenever we can see spectra towards the central parts of the galaxies, in some cases we have to stack them, but whatever we do at redshift 2 or 3, we always see signature of the absorption gas that it's having negative velocity when we are observing the high redshift galaxy, meaning that it's moving towards us. That means that there is a large amount of material being ejected from galaxies at those times. So this is kind of evidence that galactic outflows are very common at high redshift, and occasionally we can see them at late times, but not very often. The problem with these outflows is that this is not really easy to model, because as you can see, even in this galaxy, it's a process that starts at much smaller scale within the galaxy. You have to resolve small scales in order to drive these large scale outflows. So it's opposite from the inflow. Inflow is the condensation from the large scales that's driving the galaxy, but if you want to resolve outflows, you have to really pick up little pieces that are joining forces together and driving things out. So how we can model this? Well, first of all, I just wanted to say that inflow, interstellar medium, and outflows are very closely connected. And we need to account for sources of stellar feedback and their interaction even to understand the infalling gas. So to get a better picture of how these filaments are falling to the galaxies, we need to understand how much stuff and when and how it's being blown out of the galaxies. And people try to do this over the last few decades, but at the typical resolution we have in large volume simulations, this is almost impossible to do, because when we try supernovae to heat the surrounding medium, they affect way too much gas, which means that they heat it to too low temperature overall, and that this gas just cools out its thermal energy and doesn't produce any appreciable momentum, so it doesn't do anything to galaxies in practice. So we need a resolution of few parsecs to capture this momentum generation stage, where the hot gas from supernovae, such as in this Crab nebula, is actually pushing on the surrounding medium and generating this radial momentum as it's going out. And that's pretty difficult. So what we usually do in large-scale simulations, we either ignore ISM details and prescribe some sort of winds. So we tell galaxy how much it should blow out the gas. Or we prevent cooling of this remnant so that we don't have this problem of overcooling. Or we just have some feedback that is just way too weak. And all of these things can actually produce some useful galaxy formation simulations, but they won't tell us exactly what's going on at the small scales in galaxies and how the outflow is interacting with the inflow at around galactic scales. So there is a new generation of cosmological simulations where we are trying to do better. And I've been involved in the FIRE collaboration, but there are works by Agers and Krauso, Kim and all, newest Daniel Severino simulations of post-Vela are also implementing some of these important physics, and there are a couple of other groups. So I'm going to tell you a couple of details about this feedback in realistic environments, which we call FIRE. So our goal is to resolve small scales within the ISM, where we can actually implement more details of the ISM physics and resolve generation of the wind on the galactic scales. So in order to do it, we usually have resolution from around 100 solar masses or better in the best cases of dwarf galaxies to about 10,000 solar masses in the large Milky Way galaxies, and spatial resolution in the dense ISM typically from parsec to a few tens of parsecs. And most importantly, this enables local star formation and also spatial and time correlation of the stellar feedback. So Drummond and Davide are working on this model where strong correlation on space and most likely in time is needed to produce large mass flooding from galaxies. Without that, you will just have local fountains everywhere in a galaxy. And we also include local feedback processes from young stars, several that are known to be important in the ISM. So we include photoionization to regions, stellar winds, photoelectric heating, radiation pressure, and finally supernova energy and momentum. And this is what they're going to spend a little bit more time in a second. And there is no need to do any hydrodecoupling or cooling prevention. When you include some of the details of what supernovae are doing, you can actually produce self-consistent outflow from galaxies. So back to supernovae, this is probably the most important component of our feedback, but you have to include everything that is happening on the small scales in supernovae in a sense that you don't need to include only the thermal dump. You have to capture the momentum generating stage of the Seidel-Taylor phase. So proper accounting for this momentum is crucial. because thermal energy can cool out, but in the meantime, it generates a lot of momentum that's going to push material out. And if you have lots of supernovae at the same location, you can actually create a big blowout there. And evolving supernova remnant can increase original radial momentum that it got into the explosion by a large factor, by a factor of 10 or 15, depending on conditions. So what we do in fire, we actually time resolve each supernova and explicitly account for the momentum generating in Shadow-Taylor phase, cell consistently based on the local resolution and gas properties. If we can resolve Shadow-Taylor phase directly, meaning that our resolution is better than cooling radius of the supernova remnant, then we actually just let it evolve on its own. If we cannot, we impart the terminal momentum of such explosion, so there is this momentum push from the supernova happening, even if you didn't include the hot phase. So this is illustrating what can go wrong if you don't do that. So this is the terminal momentum that one expects from the evolution of the supernova remnant, shown by this dashed line as a 1D and analytic solution from Chioffi et al. And this is what would happen if you do it in a simulation with a given resolution. So this is not cosmological, those are like idealized experiments. So if you have resolution of 1 solar mass or less, doesn't really matter what you do. You can kick the particles with 10 to the 51 ergs. You can heat the particles to 10 to the 51 ergs. They're going to create this hot bubble eventually and push the gas out and reach the terminal momentum. So it doesn't really matter what you do. But once your resolution starts going out of something that can resolve this cooling radius of the supernova remnant, then it really matters what you're doing. So the fire solution is put such that it tries to mimic what's going on with this Chioffi et al. Solution. But if you just put things completely kinetically and your resolution is 10 to the 4 solar masses, you will way overproduce the momentum from each supernova. If you just put a thermal dump and don't prevent cooling, then you will way underproduce the terminal momentum from supernovae. So this is very important thing to consider. So because thermal feedback would have 10 or 15 times or 30 times, depending on the solution, less momentum than the real supernova should produce. And in fire, we try to do a careful job in capturing this property of the explosion. So what do we get when we do all this input at the small scales? So the good thing is that just with the results from Starburst 99 stellar population synthesis model, we can get really good match to stellar mass halo mass relation. And this is an emergent phenomenon of these physical processes and the implementation we put in. There is no reason to tune things or prescribe. It's possible that if the stellar population synthesis model turns out to be wrong, then we would be off here. And maybe we are missing some physics or there are some numerical issues that we are not aware of, but the match is actually pretty good without any tuning of the parameters. And the success of what's going on in this case, I will just go back for a second, where we have suppression of the star formation from the expected results from all the baryons in halos by factors of few in Milky Way mass halos and factor of hundreds in the lowest mass galaxies comes from this feedback model that creates bursty star formation history and strong outflows. So what is happening here is illustrated by the black line, just shows the star formation rate multiplied by 10, so it's on scale, as a function of cosmic time, and these red lines show outflow rates at different radii, while blue lines show inflow rates at different radii. So these bursts of star formation, and this is a very low mass galaxy in 10 to 11 solar mass scale at redshift 2, so it's around 10 to 9 solar masses or even less. These bursts of star formation are creating huge bursts of gaseous outflows outside of the halo, and they are occasionally suppressing inflow in the inner halo. At the large scale, they don't do much to the infalling gas, it's still continuously infalling, but at the small scales, they're ejecting large amount of material, lowering the masses, and polluting and doing something to the circumgalactic medium. So we can ask question, how much material is expelled through this process? And this is illustrated in this diagram that I show mass loading as a function of stellar mass at a couple of different redshifts. There is maybe some mild redshift dependence, but only at the high masses. And it turns out that required mass loading, or the mass loading we see in these simulations, can be very high. It is ultra faint galaxies, they can go to a factor of 100 or so. And this is time average, so over many bursts and over all of the star formation episodes in this redshift range. But they drop to a factor of few for high redshift Lyman-Bray galaxies. They're maybe factor of 2 or so, or even lower, depending on the mass. And by the time you reach Milky Way mass galaxies at redshift 0, they actually drop practically to 0. So these 3 points are upper limit that we plotted here, and they represent L-star galaxies at redshift 0. And the reason we plot them as upper limits is that we notice that for those galaxies, you cannot just include all the outflowing material as the outflows driven by star formation, because lots of it will just pick up regular motion of the material within the halo. So we would have to put some velocity cut to actually see what's outflowing from the galaxies. So L-star galaxies drop to 0, and the drop happens somewhere between redshift of 1 and redshift of 0. They're kind of stopping their outflows. And this is with the same feedback model in all of these systems. And I just wanted to point out this is all time average, and it includes all velocities. Okay, I'm going to speed up. So star formation changes, and it's more continuous by the time we reach lower redshift. So now this is again star formation rate, and the outflow rate that goes to 0. But the star formation is still largely driven by the infalling gas. And because there is no outflows, the disks can actually settle into very thin disk configuration and form stars in this thin disk that Shasheng Ma showed in his recent paper, and then Dusan Keres actually discussed a few days ago. And we think this is the key requirement to form late-time disky systems. If you have strong outflows in mass loading on 10, it's really hard to settle things into nice disky configuration. And infall continues, and it fuels this large late-time star formation with some help from the stellar mass loss. So at high redshift, these create galaxies that look messier, but in many cases, they still have some net rotation. This is shown in Robert Feldman's paper at redshift 2. But the redshift 0 in Milky Way-like systems, you can form extremely thin disks with a nice spiral looking structure. So another thing I wanted to point out that the infall at late times especially is not primordial. It's being recycled through many episodes of these outflows. So what is shown on this diagram on the left is this is the fraction of gas accretion at the given redshift, color-coded here as a function of halo mass. So basically for all of the halos, accretion, especially at late times, it's coming from some sort of recycling. You have to go to a redshift of 2 or 3 or so to actually get close to primordial. And lots of this accretion in more massive halos come from something that we call intergalactic transfer. So that's material that was ejected from other galaxy and it's coming onto our own galaxy. So the buildup of these massive galaxies is coming from all kinds of progenitors, not just the main progenitor and their outflows and their stripping, not just the stellar component that it's coming and merging together. And so I wanted to address a couple of questions that we raised at this conference. I think X and Nicola had these questions at the discussion. What's the baryon fraction in this kind of simulation? So in little dwarfs, the remaining baryons are only few % of the universal baryon fraction in 10 to the 10 solar mass halos. By the time you reach Milky Way mass halos, you typically get between 55 and 90% of baryons remaining within the halo. I'm speeding up. So these outflows that are sometimes leaving the halo, but lots of them actually stay in, are metal enriched. Their metallicity in the inner halo is actually not far from the interstellar medium metallicity, but at late times it's starting to drop a little bit as outflows are actually weaker and they're entramming some of the halo gas, so they're not pushing that far. And by the time you reach virial radius, lots of the stuff that is actually flowing through the virial radius is completely mixed with the CGM. So it's not close to ISM metallicity anymore. Interestingly, when we look at the fraction of the expelled metals from the galaxies as a function of stellar mass at redshift 2 and redshift 0, we find interesting trends, especially when we split this fraction into what's locked in stars, what's in ISM, and what's in CGM. And we find that at redshift 2, most of the metals are out of galaxies. So only this little fraction, ISM and stars, are still in the galaxies. The rest are either in the CGM or ejected completely from the halo. But by redshift 0, situation changes. Even in relatively low mass dwarfs, most of the metals produced are either in their extended ISM or in the stars. And only some fraction leaves the halo and only some fraction is in the CGM. So that's why we should be careful when we are doing this effective mass loading average over time. For example, we discussed this also a couple of days ago. If you just found effective cumulative metal mass loading, you would only find that it's only 2 or so, even though the real mass loading at high redshift for the gas was maybe 20 or 50 or so. So when we are comparing mass loading, we need to be careful what we are actually defining. And this amount of metals in the CGM broadly agrees with some of the high redshift and low redshift theoretical or observational inferences, but observational estimates are uncertain because of huge ionization correction, and simulation statistics are poor. So the best way to actually do some of the comparison is to do absorption lines or emission line studies, and this is a large ongoing effort in FIRE, as you saw in Cameron's talk and Billy's talk. And just the final note, similar to what Cameron was saying, when we are doing this comparison of absorption and emission line studies, we should be careful about the resolution, because even at the FIRE-like level resolution, there are still some trends when you go to higher and higher resolution. So this is illustrating at this relatively massive halo at redshift 2. So at the low resolution, which is around 10 to a few times 10 to the 5 per particle mass, you find relatively low covering factor of the Lyman limit systems, but this jumps up if you go to intermediate and high resolution. The reason for that is it's important to resolve exact details of the wind from the galaxy, but it's important to resolve all of the little galaxies in the infalling filament that are kind of pushing and spreading the filament around. So it's really hard to get all these, all these thin streams when you have strong feedback within them. So I'll just conclude very general and broad conclusions. Infall and outflows coexist and interact, and they're connected via recycling. And we need really good feedback model to capture this interaction of the infall and outflow. Without good feedback model, we can have huge disagreement about what's important, but we just won't know the answer. And outflows are more prominent in low mass galaxies at earlier times. Baryons leave halos more easily than metals. Lots of metals just stay in halos because they're rejected early on, but as feedback stops, they're just reaccreted back onto the halos and galaxies. And most of the metals are ejected from galaxies, but there is a redshift and mass dependent fraction that is recycled back. And there is a big ongoing progress in FIRE simulations specifically to get more direct comparison with observed properties of the gaseous flows around galaxies. So I'll just stop there. Thank you.
Questions and comments? Daniel?
In the movie, we just show, by the end of the movie, I see the niceties, but also see a lot of cold clamps moving around the halo. They're being agreed to the halo. Are those clamps real?
So that's something we should look in details. Yeah, you're talking about this. There was a problem of the standard SPH. This is old FIRE 1, which was done with pressure SPH, where most of the clumps that we identify as numerical were gone. But there is still definitely some clumping at late times, and we should explore if it's some sort of cooling instability of the infalling filament or completely numerical effect. I would not bet on the detailed properties of each clump for sure. Yeah, so in this particular case, there is definitely some cooling of the hot medium, and there is a little bit of cold stuff coming in, but the hot medium cooling actually dominates over these things. So
at the end, you showed the impact resolution. Would you agree in saying that even at this final resolution and all the visible feedback, would you agree that these images still have not converged yet?
I would agree that properties, especially of the CGM, have not been completely converged, and Cameron showed some of the results where we go to even one step higher resolution, and that's where he started to see some convergence in some of the ions. But the biggest problem here is when you have hot medium and the cold stuff within the hot medium. And that's the problem not only for the SPH, or now we have meshless method in FIRE 2, which is even better than this. You always have this multi-phase medium where you always have problems at the phase interface.
David, just curious if the radial gradient of the metallicity galaxies is clue to the recycling, like actually with fountains, that's the people go from the inside, where it's more powerful, goes to the outside. And so just, I don't hear about that, but just curious whether it's a...
Yeah, so we...
Can you say something about the radial gradients?
Yep, I mean... Yes, so Shashank had a recent paper on the metallicity gradient, and he showed that the phases where you have strong outflows, you tend to erase metallicity gradient. So you need to phase where it's more quiet without much outflows happening to actually build up negative or positive, depends how you count, metallicity gradients. And he showed that at higher redshift galaxies that just didn't have currently outflow can build it up, but then it's often destroyed. But at late time L-star galaxies typically do have some gradients. So that is definitely lack of gradients. I would say it's suggesting that there is some activity happening with the galaxy that's erasing stuff. Yeah, I don't know if you can like exactly detail profiles it can distinguish between different feedback models, but that's something to look at.
The ratio of the outflow to the starvation rate. That's load factor must affect that. But if that's load factor is less than 1, it's hard to see how you can miss it. If it's much greater than that, then of course you smooth it all out very hard.
Yeah, I mean, it's possible that we could get something more quantitative out of it. Right now, we just show an example of a couple of cases where you have strong winds or you don't have it, and that definitely changes the metallistic gradients. Yeah, I mean, it would be great to have like 50 L-star galaxies, not like 3 or something.
Okay, I think we have to stop for a brief lunch. Notice that the schedule says we should be back about 1:35. So let's thank all the speakers of the morning.